We have a short review here of Chapter 8. Chapter 8 with our hypothesis testing. And our hypothesis testing, regardless of whether we're testing the mean, the variance, the standard deviation, proportions, all revolved around 5 steps. In step number 1, we write our 2 hypotheses. And we identify a claim. Our 2 hypotheses are a null hypothesis, H sub 0, and an alternative hypothesis, which is H sub 1. Our null hypothesis always contains the equal to sign. Our alternative hypothesis is typically, I won't say every single time, but it's typically what we write first, and that's the inequality, the less than, the greater than, or the not equal to. Our alternative hypothesis here is what we based our right or left-tailed or two-tailed test on. If we have an alternative of less than, we have a left-tailed test. If we have greater than, we have a right-tailed test. And if we have not equal to, we have a two-tailed test. And then we identify one of these as our claim. Whichever one's our claim, then is what we're investigating through our 5-step process. So step number 1, we are our 2 hypotheses, identify the claim, remembering our null hypothesis always contains the equal to sign. In step number 2, we find our critical value or critical values, depending on whether we have a 1 or 2-tailed test. Those values come from one of our 3 tables, table E, which is our z-score, table F, which is our t-score, or table G, which is our chi-square score. Okay, so depending on whether we're testing the mean, proportion, or variance or standard deviation here, we use one of those tables to find our critical values. Step number 3, we calculate our test score. Our test score is either a z-score, a t-score, or a chi-square score as well. That's what we're going to compare to our critical values up above. In step number 4, we either reject the null or we do not reject the null based on what our test score and our critical values tell us. In step number 5, there either is enough evidence to support the claim or there is not enough evidence to support the claim. Okay, so those are our 5 steps in the hypothesis testing process. A little variation from one type of problem to another, which we'll discuss here in just a second. But those are our basic 5 steps. Write our 2 hypotheses, identify a claim, find our critical values from the table, find our test score from our formula, use that information to either reject or not reject the null, and use that to draw a conclusion about our claim, where we can support it or not support the claim. As a side note here, test time, there will be 2 points involved here in number 1. One for writing our 2 hypotheses, and another point for identifying our claim. So make sure for each problem you identify your claim. There are a point here for finding our critical value, a point for our test score, a point here, and a point here. So each one of these 5-step process problems come test time is worth 6 points. So make sure you label all 6 steps or all 5 steps as you go down there in detail, because each one does have a point value on the test come tomorrow. Once we have that 5-step process in place, we started with testing of different values, and we started out with the mean. When we had the mean, we had 2 different directions we went. Okay, mean will spell out the word mean, or it might use the word average, but that should be, I hope, fairly obvious as you read through a problem. We'll be testing whether the population mean is this number, the sample mean is this number, and so forth. But once we know we're testing the mean, which is this symbol right here, our population mean, mu, we either were given the population standard deviation, or we were given or calculated the sample standard deviation. And that's the one criteria that determines what direction we go. So with population standard deviation, it will probably be spelled out one way or another. I'll underline, as we went through these in our notes, underline the population standard deviation was this number. It might also just be given to us as sigma. Sigma is our population standard deviation, so if that number is given as 6.5, that's our population standard deviation. Or it might say from past studies, the standard deviation is known to be this number. So in one of those forms, once we determine we have the population standard deviation, that tells us to use table E or our z-score for our critical value, or values, depending on whether we have one or two tailed tests. We should be pretty well versed in reading table E by now. We've read it since chapter 6, so 6, 7, and now 8 we've used chapter E. But in case we forgot, table E always measures the area to the left of our z-score, so keep that in mind as we go to look up values on that table. Population standard deviation, again, tells us to use table E for our z-scores. Some of those common ones that you'll see quite a bit of, 1.65, 1.96, 2.58. That's not an all-inclusive list. We still have to be able to read the table, but those do come up quite often. Okay, so one more time, population standard deviation is the one thing that tells us to use table E. If we have the sample standard deviation, and again, that'll probably be spelled out a couple different ways. Sample standard deviation is S. A sample of 10 had a mean of 14 and a standard deviation of 2. Well, our sample of 10 had a standard deviation of 2. Or we might have a list of numbers we have to plug into our calculator and calculate our one variable stats. Off of our one variable stats, we pull off S sub x, which is our sample standard deviation. So in those scenarios, once we've established that we have the sample standard deviation, we use a different table, table F, for our critical values, and table F is a t-score. Okay, so again, sample standard deviation tells us to use table F, t-score for our critical values. And when I say those critical values, in both scenarios here, our critical values are in step number 2 of our 5-step process. At least that's where we have placed those, step number 2. Table F is based on degrees of freedom. We should know by now degrees of freedom are simply our sample size minus 1. It's also based on alpha. Alpha is one of 3 of our common ones, 0.01, 0.05, or 0.10. And whether or not we have a 1 or a 2-tailed test. Those columns are at the top, or not columns, those rows are at the top of table F. So if we have a right or a left-tailed test, that means we have a 1-tailed test. We use the 1-tailed row along with our degrees of freedom to find our critical values. If we have a not equal to sign, then we have a 2-tailed test. We use a 2-tailed row along with alpha and our degrees of freedom to find our critical values there in step number 2 and plug into our curve, with our curve having 0 in the middle. Left-tailed test will be on this side. Right-tailed test on this side. 2-tailed test would include both of those. But there's the bottom line here for our mean. We use 2 different tables. If we know the population standard deviation, we use table E. If we know the sample standard deviation, we use table F to find our critical values. And then we move on to the rest of our hypothesis testing process. In step number 3, we calculate our test value. For our population standard deviation, it's the sample mean minus the population mean divided by our population standard deviation over the square of our sample size. I'll put our parentheses in there to remind us of our order of operations. If we had or we're using table F, the calculation is pretty much the same. It's labeled as a t-score, but it's still the sample mean minus the population mean. We're dividing by our standard deviation. Our standard deviation is the sample, so it's S and the square root of our sample size there as well. Putting our parentheses in for our order of operations. So you'll notice those two formulas are essentially the same thing. They have a different label, a Z versus a T. That's kind of a cosmetic thing, not a big deal. But the one big difference is we're using the population standard deviation in one and the sample standard deviation in another. And once we have those, we compare those in step number 4 to determine whether or not to reject or not reject the null. And that boils down to where does our test score lie in relationship to our shading. I can't draw a curve. Third time's a charm, hopefully. Not much better, but a little bit. So we have our 0 there in the middle. So let's say, just for our example here, we have a left-tailed test. So we have shaded that left tail based on the alternative hypothesis being less than. Okay. Once we calculate our test value in this step, if it lies in the shaded area, so it lies anywhere in here, my test score here or here or here, somewhere in here, that tells us to reject the null. If it lies in the unshaded area, so our test score lies anywhere in these areas, then we do not reject the null. Okay, so there's how we make our decision. Basically, I'm going to go back up to here. I'm going to put our null hypothesis here. We have our alternative here. We shade based on this inequality, so we shade based on the alternative hypothesis. So anything that lies in the shaded area tells us the alternative hypothesis is true. Anything that lies in the unshaded area then tells us that the null hypothesis is true. So I'm just going to write that down. Shaded area is the alternative hypothesis, and the unshaded area is the null hypothesis. And then once we have that determined, we have to look to see where our claim is. If we identify our claim as our alternative and we reject the null, by rejecting the null, we're saying the null is incorrect, which means the alternative is correct, which means then the claim is correct, so there is enough evidence to support the claim. If we did not reject the null, we're saying the null now is true, which means the alternative is false, which means the claim then is also wrong, so there is not enough evidence. So the bottom line is, don't just make a blanket statement about comparison of these two. Don't lump these two together. Make sure you understand where your claim is and what you did with the null hypothesis in order to decide what to do with a claim to support or not support that claim. So that should cover our mean. Once we had the mean in place, we then moved on to proportions. Proportions will not always use the word proportion. Sometimes it will, but sometimes you might see a percentage, or you might see a number out of a total, where you have to calculate your own proportion, which would be our p hat or our sample proportion. But once we establish we have a proportion by either a percentage or a number out of something else, again here, one that comes to mind is we had 500 nursing applications and 60 of those were from men. So 60 out of 500 were from men. That's a proportion of number of applications that were from men. So our p hat, or our sample proportion, is 60 divided by 500, or 0.12. So there will be times you have to calculate your own sample proportion. But if we start our five-step process, let's not start our process yet. Let's also remark here that our proportions all use table E. Those are all Z-scores. Blanket statement, regardless of what type of proportion we have, they all use table E, Z-scores, the 1.65, the 1.96, the 2.58. Those types of numbers from our table. Again, we should be pretty well versed there on finding those. Again, as a reminder, our table measures the area to the left of a Z-score. But our first just cosmetic change, When we write our two hypotheses, we do use the symbol for proportion. Our last ones we use the mean. Here we're now using proportions. So that is a cosmetic change. Step number 2, we've already said our critical values come from table E. So there's not a switch there from our previous work. That should be pretty straightforward. Our test score formula does look different. It uses our proportions. So it's our P hat, which is our sample proportion, minus P, which is our population proportion, and we divide by P times Q over N. These are our population values, so if P is 0.1, 0.1 and 0.9, that's for 0.3, 0.3 and 0.7 and so forth. And notice that is entire calculation underneath the radical, so the N is being divided into P and Q under that same radical. Order of operations wouldn't be a big deal here. We put parentheses around here and then divide by our radical here. This formula is on our important formula sheet, so you don't have to have that memorized, but you do have to be able to plug that in and know what those values stand for. And then once we have those, same decisions for rejecting the null, not rejecting the null, supporting the claim, not supporting the claim. So there's our big change, so to speak, is in step number 3. We have a different test score formula, and we also have this I label as a cosmetic change, working with proportions. Our symbol change up here, we use P instead of mu. Then we went on and we had our testing for variance and standard deviation. This testing process uses table G, which is a chi-square score. Okay, that table is actually called a chi-square distribution. Much like our table F or our T distribution, this is based on degrees of freedom. Degrees of freedom still sample size minus 1, so we should be pretty well versed on that. We used table G back in chapter 7 as well. I guess we'll start with our step number 1, another cosmetic change. Here we're using either the symbol for variance or the symbol for standard deviation. Same thing with our alternative, variance or standard deviation, so we're not using the mu or the P. A cosmetic change here with our symbols. Still running our inequalities at equal to sign over here. Step number 2 is where we will see a change. If we have a right-tailed test, we'll use alpha as the column at the top of our table. It will be on the right-hand side, so that kind of corresponds to a right-tailed test. Alpha is going to be on the right side of table G, along with our degrees of freedom to find our critical value. So it's a right-tailed test on the right side of our table. If we have a left-tailed test, we use 1 minus alpha as our column at the top of the table. And that will give us a number like 0.99 or 0.95, something like that. Those numbers are on the left side of the table, so hopefully that makes it easier to remember. Left-tailed test, we use a column on the left side of the table, along with our degrees of freedom to find our critical values. And finally, if we have a two-tailed test, we're going to find 2 columns at the top of the table. One of those is alpha divided by 2, and the other is 1 minus alpha divided by 2. This will be on the right-hand side. This will be on the left-hand side. That brings up another interesting note about our curve here with our chi-square. With our T distribution, our Z distribution, table E and table F, we always had 0 in the middle, so we had negative values on this side. I'll put 0 in the middle. Negative on this side and positive on this side. With our chi-square, we start at 0 over here and work our way up, so all of our critical values are positive. So keep that in mind as you put those on the table or on the curve. Right-tailed, use a right-hand column, which is alpha. Left-tailed, 1 minus alpha, which is on the left side of the table, left-hand column, along with our degrees of freedom. And two-tailed test, we use alpha divided by 2 and 1 minus alpha divided by 2. From there, our test score formula is also on our important formula sheet. It's our sample size minus 1 multiplied by our sample variance divided by our population variance. So even if we're testing standard deviation, we still use the variance values in our calculation. So our chi-squares are based on variances, so we have to use those in our calculation as well. So one more time, sample size minus 1, sample variance divided by population variance. If you have the standard deviation, we should know by now we have to square it to get our variance. And then we follow up with our rejecting or not rejecting the null and supporting or not supporting our claim in step number 4 and 5. And there's our 5-step process for each of those. One other item to go back over, there is one problem on our test that asks us about p-value. So what's going to happen, let's say in problem number 2, we went through what I call our traditional method, the information I just went over, and we went through our 5-step process and found our critical values, our test score, and so forth. So we were in problem number 3, it's going to say find p-value from number 2. Okay, so we have to look at a couple things here. Number 1, we have to look at our alternative hypothesis. If it's a one-tailed test, we'll find our p-value one way. If it's a two-tailed test, we have to double it. So it all depends on whether it's less than, greater than, or not equal to. The first two are a one-tailed test. We just find our p-value. It's pretty straightforward. If it's not equal to, we're going to have to double our number we get down here to find our p-value. So that's the first thing we look at is one-tailed versus two-tailed there in our alternative hypothesis. Then we go back here to step number 3 to find our test value. So our test value is, say, 1.75. Okay, we go to our table, look up the area for 1.75, and off of our table we find 1.75 to be 0.9599. Okay, with this situation, our alternative hypothesis would probably be greater than, so in our curve, we would have shaded the right-hand side. The 0.9599 is the area down to the left, so we'd have to subtract it from 1, and that would give us 0.0401. Since we have a one-tailed test, that would be our p-value. If we had the same scenario, but it were a two-tailed test, we'd simply have to double that to get our p-value. Okay, so p-value is just the area in the tail of the curve based on the test score that we got there in step number 3. So there is one of those on the test, very similar scenario. I'm not going to tell you whether it's greater than, less than, or not equal to, but you have the idea here on how to find that based on the area of the curve. We know how to read table E by now. We'll only use the p-value method for a mean, and only with table E, so we don't have to worry about table F or table G. That's a completely different process. So we won't have to worry about those just with table E, and there is just the one problem there. And that should pretty much cover what's on the test.